I hope you're able to see my screen.
Yes, sir.
Yeah, thank you. So I'll quickly explain the flash separator. So anyone have any idea what is flash separator? On the student side, anyone have any idea? Have you heard about flash separator in mass transfer course or not?
Sir, we used it to separate the gaseous and liquid phase.
Yeah, we used to separate the gaseous and liquids, especially if you have a liquid mixture, which is volatile, which has we have a liquid solution. This liquid solution contains two miscible components. Miscible components, the components. Two miscible components, and both components or boiling points of the components are different. Or it's significantly different. We can use distillation column, flash separation, all are comes under the same umbrella. So what we do in the flash separator, what the difference from the typical distillation column or something? In a flash separator, we take the liquid solution, miscible liquid solution, right? It has two components, A and B. This this liquid solution is feed or first of all heated to certain temperature. So I'm just putting a heat exchanger. So it's heated to certain temperature. Then it introduced to where? After heating to certain temperature, this will be introduced into which one? Any guess from the students? In a flash separation, a liquid solution or liquid mixture is heated to certain temperature at certain pressure, then introduced into which one? What will happen after this, after heating? Heated to certain temperature, then it will introduce to an empty chamber. It is introduced to an empty chamber, like a flash drum. It's like a flash drum. So it's introduced into an empty chamber. Empty chamber. So this is empty chamber. It has certain high volume. Now when you heat it to certain temperature, let's say you have taken a liquid at room temperature and you have to heat it to certain temperature, what will be there? Like it will have both after heating certain temperature, right? If introduced to an empty chamber, what will happen? I have a liquid mixture, a liquid solution, heated to certain temperature. Then I have introduced into an empty chamber. What will happen to the pressure of that liquid solution into that empty chamber?
Decrease.
Decreases. So when pressure decreases, what will happen? Or let's say we have a vessel where we have introduced liquid, and the pressure inside this chamber is decreased. When pressure decreases, what will happen to the boiling point of the liquid solution? Will it boils more or less?
More.
It boils more, vaporizes more, right?
Yes, sir.
Yeah. Suppose we take water. Water boils at 100 degrees centigrade, 100 degrees centigrade at 1 atmosphere pressure. Same water boils lower than 100 degrees centigrade, boils at lower than 100 degrees centigrade when the pressure is lower than 1 atmosphere. Are you agree with me? This is a well-known statement. Water boils at 100 degrees centigrade if the pressure inside the chamber is 1 atmosphere. Same water boils at lower than 100 degrees centigrade when pressure is lower than 1 atmosphere. So we have a liquid mixture heated to certain temperature. Now we suddenly flashed. Flashing means what? Allowing that one to enter into an empty chamber, allowing that liquid mixture, the hot liquid mixture, into an empty chamber. We are just flashing. So when you flash it, since the pressure is lower than the whatever pressure we are heating, so the pressure will reduce, and the same liquid mixture boils a much higher, boils at much higher when introduced into the flash chamber, because the pressure is reduced. Now we get two streams. What are the two streams come from this one? We get two streams come from here. One is what will come out from here? What will come out from the top? Other students should answer. As I said, you will vapor, yes. Whatever you answer, whatever responses you give, it counts, because this is a continuous assessment. Okay, if nobody answer, then I will have to call the names, which I don't want to do it. So we get vapor from the top, and we also get another component from the bottom. So we get another component from the bottom. That is liquid. So let's say this is Ti, and the vapor temperature, let's say Tv, and the liquid temperature is TL. Now the question is Ti, Tv, TL are same or different? Is Tv, Ti, and TL are same or different?
Same.
Different.
Same. Why do you think it is same, Soumik?
Because sir, when pressure drops, it is boiling on itself and no extra energy is provided. So temperature should not change.
So no extra energy is provided, so temperature should not change. But here, is vaporization is taking place or not?
Yes, sir.
So, so when the pressure of a vapor changes, will the temperature changes or not? Let's say, leave it for the example of, let's say you have only vapor in the container, and the pressure inside the vapor container changed. Will the temperature changes or not? Just assume there's a container, it contains gas, and we have changed the pressure. Will the temperature remain same or changes? Changes. So if it is only liquid, you're absolutely right. When when even though we are reducing the pressure, the boiling, it may boils more, but the boiling temperature doesn't change. But if there is a vapor, when there is a pressure change, the temperature also changes. Temperature also changes. So since as soon as we introduced here, we are heating, the liquid is heated, right? It's set in temperature, and there will be partial vaporization possible. The partial vaporization can happen. If it is only reached the saturated liquid state, then even then, as soon as you flash into the flash column, you will have vapor and liquid come out. And since vapor is subjected to the lower pressure, right, and the temperature slightly changes. So Ti, Tv are not same. Ti, Tv will not be same. Because even if you assume Tb behaves like an ideal gas state, PV equal to PV is proportional, PV equal to RT. So when pressure changes, correspondingly volume and temperature changes. If we keep one thing constant, then we have a direct relationship. But if we don't keep one thing constant, still both changes. So that's why Ti, Tv, TL are not same. Ti, Tv, Ti will not be equal to Tv. Now, how do we estimate? Let's say I know TV and TL. For example, I know TV and TL at equilibrium, at equilibrium, at thermal equilibrium, TV equal to TL. At thermal equilibrium, TV equal to TL. Now, how do I find out? Let's say I know TV and TL. Let's say I know TV and TL. Will I be able to find out vapor composition and liquid composition? Let's say I know TV and TL. Will I be able to find out vapor composition, liquid composition?
Sir, from the phase diagram, maybe.
From the phase diagram. Is it phase diagram? Something else. Names like maybe you intend same.
It's a TXY plot.
Yes, TXY plot. Correct. That is vapor liquid equilibrium data.
Yes, sir.
Yeah. So if we know TV and TL, if we have TXY graph, if we have the TXY graph, that is vapor liquid equilibrium equilibrium data. If we have vapor liquid equilibrium data, and since we know TVTL, we'll be able to find out the vapor composition and the liquid composition. I'm sure you all done the flash calculations. If we, because we don't know temperature, we don't know, we like in flash calculations used when we don't know the temperature. when we don't know the temperature. We don't know TV and TL value. Usually we don't know directly TV and TL value. So we use the flash calculations, what you've done in mass transfer. What you've done in mass transfer. If we know TV and TL, assuming the equilibrium TV equal to TL, if from the TXY plot, we get the vapor liquid equilibrium data. So typical TXY plot will be looks like this. I'm sure all of you remember it, but let me discuss once. So this is y-axis, and this is an x-axis. Okay, and we will take two y-axis. Both are same. Both sides we have boiling point. Both sides we have the boiling points only. Oh, sorry. Boiling points in the y-axis. Mole fractions. Mole fraction of what usually we represent in x-axis. Mole fraction of what? We have two components A and B. What will we represent in x-axis? Mole fraction of which one? High volatile or low volatile?
More volatile.
More volatile component. So mole fraction of more volatile component will be mole fraction of more volatile component will be represented in x-axis. So that could be if mole fraction of more volatile component in liquid is represents with x, and in vapor represents with y. In vapor represents with y. So x and y both are 0 to 1. The ranges from x and y values ranges from 0 to 1. So both are put in x-axis. Y-axis we have the boiling point. Now maybe someone else, for those who not answered yet, the boiling point of more volatile component is higher or lower than the boiling point of lower volatile component. We have A and B. A is more volatile, B is low volatile. Which of the will have lower? So the more volatile component, more volatile component boiling point is lower, whereas low volatile boiling point is higher. So see at 0, so this is 0, right? Since mole fractions, this is 0. So this is 0. This is 0, where since we are taking the mole fraction of more volatile component, if A is more volatile component, A is 0 and B is 1. And here, this is 1. That means purely more volatile component is there. So the boiling point of this is this will be at this point because this is x equal to 0. X means the mole fraction of more volatile component is 0. That means low volatile component will be there. They will have higher boiling point. Then we have another boiling point. X equal to 1 means it is fully high volatile component is there. Fully high volatile component there, which have the lower boiling point. So if you do the vapor liquid equilibrium data, typically it looks like this. Typically it looks like this. So the bottom one So the bottom one is liquid composition, and the top one will be vapor composition. The top one will be vapor composition. I hope you all would recollect some of the things what you learned in mass transfer other courses. So let's say I have given this graph. Now from this graph, how I will be able to find out the vapor composition, liquid composition? Any student could give an answer to me. Now we have the Txy graph. I just shown Txy graph. So in y-axis is temperature, that is boiling point temperature. No, just temperature, not the boiling point. This is just temperature. Temperature. Any one student would answer me. Let's say I have graph. We already have the answer. Right. So maybe Jyotiraj messaged. Let us see. Yeah, that is true. Now, how will you find out? How do you draw a line? How do you draw a line from the graph to find out x and y? Here, probably his mic is maybe not working, so it's fine. So we know the temperature, right? We know the temperature. At the temperature, we draw a line. At the temperature, we will draw a line. This temperature will be Tv equal to TL. This temperature will be Tv equal to TL. So where this line touches, this lower line, this liquid line, that will be the corresponding liquid composition. Where it touches the vapor line, that is the corresponding the vapor composition. That is the composition or the concentration or the mole fraction of more volatile component vapor, and this is the composition of, or this is the mole fraction of more volatile component in the liquid state. So that way we know vapor composition, liquid composition. But if we don't know TV and TL, then we have to do the flash calculations that you have learned in mass transfer. I will not repeat that here. So now, how do we find out? How do we get this TXY data? I have drawn TXY data. Probably you all would have, probably you all would have known. How do we get this TXY data? From where we get this TXY data? How do we get this TXY data? Any student? Those not answered yet may answer it. How do we get this TXY data?
For many different temperatures, we find the value of x and y, and then we plot the values of x and y.
How do we get x and y? That is true.
When we draw the horizontal line for the temperature, at the bubble point, that where it intersects the bubble point curve, it is the x of the more volatile component, and where it intersects the dew point curve, it's the y of the more volatile component.
Yeah, that is correct, Sanskar. Now, how will you get this bubble point curve and how will you get the dew point curve? My question is that one. I hope you understood.
Yes, sir.
Yeah, t versus y, t versus x data. How we'll get it? Probably have you learned that in thermodynamics? Maybe you forgot the formulas.
Sir, I think it is, hello.
Yes, Subhajit.
There was something called Margulis equation and Van Laer's equation in thermodynamics.
Right, Margulis and Van Laer equation. That is what Margulis and Werner equation used for what kind of solutions?
We use it to get the VLE data.
Are you sure?
Yes, sir. Like there was some term called gamma, and we used to find it
Yeah,
from the.
Margulis is basically to give the Gibbs excess energy G by RT versus X versus Y. From that, we calculate chemical potential. But they're primarily predominant use for the non-ideal liquid mixtures. That would be the little tougher case. Now, for a simple case, let's say the liquid mixer behaves like an ideal liquid, ideal solution. The vapor mixer behaves like an ideal gases. For that, we use Raoult's law, right? For that, we use Raoult's law if we take an ideal case. Let's say we know the Raoult's law. Maybe I am giving the clue. What is Raoult's law? Can anyone say?
The relation between partial pressure and vapor pressure.
Relation between partial pressure and vapor pressure. So what is that relation?
So
Sayan?
like the vapor partial pressure is equals to vapor pressure into the X liquid mole fraction.
Right, very good. Raoult's law, which gives relation between partial pressure and vapor pressure. Very nice. So partial pressure equal to liquid mole fraction, that is X, into vapor pressure of the vapor pressure. Now partial pressure can be written as what is the relation between partial pressure and total pressure? Let's say I wanted to express in terms of total pressure.
Partial pressure is mole fraction in gas multiplied by total pressure.
Very good. So the mole fraction or more volatile component in vapor multiplied by total pressure. So this is the Raoult's law. Now here we have Y. This is Y into, I will just say P underscore T, total pressure, equal to X into P sat, saturation pressure. Now we have X and we have Y. Now from this, are we able to calculate X versus Y data if we know T? Suppose I know T and we have T. Suppose we have P and we have T. And are we able to find out X and Y?
Yes, sir.
Yeah. How?
So like we can find the value of P saturation using Antoine's equation if we're having the temperature.
Right. Very good. So if you have the temperature, we can find out P sat. We can find out P sat using Antoine equation. So once we know the P sat, so we know temperature, we got the P sat, and if you assume different X values, let's say 0, 0.1, 0.2, 0.3, 0.4, these are the different X values. We can calculate the corresponding Y value. How? Y equal to X into P underscore sat by P underscore T. So we know the total pressure and the pressure is fixed. The total pressure is fixed and the temperature varies. The temperature varies. Then temperature varies. Then at different x values, we can get the corresponding different y values. If you want to generate pxy data, then we have to use little bit iterative procedure, or we have to use little bit difficult calculation. But I'm sure you have all learned this in thermodynamics. I don't want to again repeat all those things. The reason you may say why I'm teaching this, I wanted to show you these all calculations can be done in a very quick manner using this process simulator. And we can also automate all these things. We can write our own codes. We can write our own process simulator software, which I will show you a little later, maybe after 1 or 2 weeks. So we get pressure and we get varying temperature. Then now here I'm saying that I am varying only one variable. I am keeping one variable is fixed. One variable is fixed. I am only varying one variable. Now, if we, for some components, let's say for the properties of single component, I need to know two variables. Let's say pressure and temperature, or pressure and volume, to find out the property. So here, either one property we vary, or we have to vary two properties, which determines the number of dependent variables or number of independent variable. So how do you find out what is the number of dependent variable? Number of dependent variables. Which equation gives us, for a given system, what are the number of dependent variables or number of independent variables? I think independent variable. Which rule, which law tells us number of independent variables? Phase rule, yes. Phase rule tells us number of independent variables. This is from the phase rule. This number of independent variable corresponds to degrees of freedom. Degrees of freedom. This gives the phase rule. If you want to model any system, right? If you want to model any system, it's not just a chemical process. If you want to model any process, it could be marketing analytics or banking sector, or it could be anything. We always have to know which of the variables are controlling, We have extensively used this concept, which parameter is controlling, which parameters are the independent or dependent parameters. In reactions, we see limiting reactant, or whether temperature controls, whether pressure controls, or the fractions control, what parameters control. This is the whole modeling of a system. This concept is same. Even if you do the modeling of a banking, let's say sales in a shop, we have to know what are the parameters driving it. Now the concept remains same. How we approach varies from the phenomena to phenomena, right? So here we get the phase rule. So what is the phase rule? Anyone tells me what is the phase rule? Expression of the phase rule. Let's say degrees of freedom F equal to
C plus P minus 2.
C plus P minus 2. Are you sure?
Sir, it's C minus P plus 2.
Yes. C minus P plus 2. Correct. C minus P plus 2. So suppose you take a single component. Example, water at room temperature. Water at room temperature is liquid. Now water at room temperature, or well, let us say water at 35 degrees centigrade. What is the state of water at 35 degrees centigrade? Water is at 35 degrees centigrade. I have given this information. What is the state? Can anyone define the state? I have mentioned like this. Water is at 35 degrees centigrade. What is the state? Not stage, sorry, state. Are we able to tell the state of water at 35
No,
degrees
sir.
centigrade? No, we cannot tell. What else we need to know?
Pressure.
Yes, we need to know the pressure. Water is at 35 degrees centigrade and atmospheric pressure. If we tell both, then only we will be able to tell the state. What is the state? We can easily say, yes, this is a liquid state. So here, to find out the state of liquid, we need to know two properties. That means we need to define minimum two properties that we can tell from the degrees of freedom. So number of components is 1, number of phases is 1 plus number of, this is 2. So this comes to be 2. So the degrees of freedom is 2. The degrees of freedom is 2. That means for a single component, we need to define two properties. Unless you tell two properties, we cannot define the state of that one. We cannot estimate the properties of that one. So if you take a mixture of components, let's say liquid is in vapor liquid state. And the liquid is in vapor liquid state. Liquid is in vapor liquid state. At that time, liquid is in vapor, liquid is in equilibrium with vapor and liquid. Vapor. We have a single component, let's say water. The water is present in a chamber where the liquid is in contact with a vapor, liquid vapor, or water vapor, and both are in equilibrium. Now, what is the degrees of freedom? We have component 1. Because only one component is there. The number of phases are 2. And plus 2. So the degrees of freedom is 1. That means you need to know only one property to define the state. So if you know pressure, we can define the state. If you know temperature, we can define the state, because that's why it comes here. That's where it comes. If you know pressure, we can easily know suppose if you know temperature, we can easily know the saturation pressure, then we can do the rest of the calculations. That's why it is called TXY or PXY. That is called TXY or PXY data. So I hope you are understanding how this degrees of freedom is explained. So for any component, for a single component, even if you take a single pure component, we need to know two properties. So the basic properties P, V, T, 2 out of these 3 usually defined. 2 out of these 3 usually defined, but not necessarily only these 3. Not necessarily, we should not think that only pressure, volume, temperature. It could be anything: pressure, volume, temperature, entropy, internal energy, or enthalpy. Any property we define, any two property define, we'll be able to estimate the properties of the single component. So that is the whole exercise of thermodynamics. The whole exercise of thermodynamics is that if we define any two, we will be able to estimate the rest of the properties. So a lot of derivations, lot of simplifications are done, that if I know two properties, usually pressure and temperature, I should be able to estimate volume, I should be able to estimate entropy, I should be able to estimate enthalpy, I should be able to estimate internal energy, and whatever latent heat of vaporization, delta H. So the interrelation, the derivations between all the properties are derived. All the properties are derived. Now, if I know pressure and temperature to estimate the volume, what are the common things we use in thermodynamics? Anyone remember? Suppose if I know pressure and temperature and I wanted to estimate the volume, whether it's gas or liquid or vapor liquid, what are the things we use in thermodynamics? Little bit, maybe. I hope you understood my question. Maybe I didn't present my question very well. Let's say I have a single component and I know pressure, temperature. I want to estimate the volume of that one. Theoretically, how do we do it in using thermodynamics?
Sir, we use equation of states.
Yes, very nice. So we use equation of state. So we will use equation of state to find out the volume. Equation of state. So what is the ideal equation of state?
Ideal gas equation.
Ideal gas equation. So PV equal to NR. If I don't use N, the V volume will be specific volume. So RT. RT. So using this expression, if I know pressure, temperature, suppose if I know if pressure and temperature is known, using this equation we can calculate volume, that is RT by P. RT by P. Now what is the, at what conditions this ideal gas equation valid? At what conditions? Lucy, you may answer. At what conditions we can approximate that we can say ideal gas equation behaves very well or gives good prediction?
When compressibility factor approaches 1.
Right. So
like for high temperature and low pressure.
Very nice. So ideal gas equation can be used when the compressibility factor is 1. Approximately when the temperatures are very high or the pressures are very low, then we can approximate it. We can use comfortably ideal gas equation. And he's rightly pointed out, for other conditions, if the compressibility factor is lower than 1, definitely the ideal gas equation will not predict very well. So we have non-ideal gas equation, that is PV equal to ZRT, where Z is compressibility factor. So Z equal to PV by RT, which is equal to, how do we express the compressibility factor? We have another equation of state called virial equation of state. Using that, can anyone tell me how the Z expression looks like? Z equal to P by RT equal to. I know some of you might not remember, but those remember can answer.
Sir, I guess it'll be a polynomial in pressure.
Polynomial in pressure or polynomial in volume?
Yes.
Both. Depends upon requirement. This can be expressed in polynomial of pressure or polynomial of volume. Both way we can done. So it will be like 1 plus some constant by V plus some constant by V square plus some constant D by V to the power of 3. This is one approximation. This can also be approximated as Z equal to 1 plus B into P plus C into P square. This way they approximated it. This way of approximating, or this way of fitting the data, or this way of getting the data is very old technique. Nowadays, we have a lot of fitting linear regression algorithms. You might think that these are new, but this is very old, or back to 8 years old techniques. Getting the data using the regression techniques, whether it is simple linear regression or multi non-linear regression. This is very old in chemical engineering. Actually, in thermodynamics, if we study very well, a lot of statistical techniques are used. And if you really understand these processes, mm, you will be really surprised that modern statistician will not even think of the way the kind of statistical fitting was used by chemical engineers back in early generation of thermodynamics. Very complicated. We are able to fit a properties of a component at all temperatures, at all pressures, at all conditions, critical conditions, vapor conditions, saturation conditions, highly volatile, low volatile. They generated a unique equation that can estimate the properties of all conditions. You can see kind of statistical fittings they use before they do derivations. It was really amazing. Sometimes when I think of this, kind of thoughts they got, kind of inspiration they got was really amazing. Those scientists like Gibbs and other things, it was really superb. But these techniques are inbuilt. Like chemical engineering get to know these linear regressions and all very naturally. There's not just that they might change the names of the some of the algorithms, but the techniques or whatever we do is very natural, very common. Of course, some of the algorithms nowadays people uses slightly different. Some of the maybe some of the advanced techniques, but as we go through, you will see that some of the fittings, some of the linear regression techniques were very common in chemical engineering. So this is the real gas equation of state. So what is the use of this? Suppose if you know B, C, D, we will be able to predict the compressibility factor. We will be able to predict the compressibility factor. Then we will be able to estimate the volume. We will be able to estimate the volume. So once you know pressure, temperature, volume, we have many correlations that we can estimate: entropy, enthalpy, internal energy, which I will show you after some time, all the relations between these two. So since we are able to estimate the properties theoretically, this using the equation of state, or let me also show you. So for a pure component, this is the phase diagram. This is the phase diagram, PV diagram. This is the PV diagram, and this gives, let's say, this gives how this at a isothermal lines, isothermal lines, constant temperature lines. At this constant temperature, we can estimate the properties, and we can also know the state of that one depends upon the pressure and volume. So that is the PV diagram, and this is PT diagram at a constant PT diagram, and this is PVT diagram. This is the PVT diagram, and you can see this is the constant pressure line, and this is the constant temperature lines. These are the constant temperature lines, and this equation of state supposed to define a line equation that can generate this three-dimensional plot. This equation of state, what we are just seeing, that is able to describe this three-dimensional plot using a simple expression. The whole idea is we have this data, PVT data. This is three-dimensional, very complex. This whole complex data, they're trying to express simple mathematical equation. They're trying to represent this whole data into a simple mathematical expression. It could be Weyl equation of state, or it could be Van der Waals equation of state, or it could be RK equation of state, or it could be many Pitzer correlation. There are multiple people have generated these correlations based on this data. So that is where the equation of state comes. equational state is supposed to predict this, represent this three-dimensional plot, using a simple mathematical expression. Of course, they have made assumptions. Different people have made assumptions, and they have developed different equational states. So you might have seen in thermodynamics, Redlich-Kwong equational state, Sayovi-Redlich-Kwong equational state, Peng-Robinson equational state, Re-Kessler equational states. So different people have taken different types of the components and they have studied. So for example, Peng-Robinson, they have studied extensively the hydrocarbon components. And if you take the Redlich-Kwong equational state, they have studied the simple organic solvents and some of the inorganic solvents. Like this, they have taken certain group of liquids and they have done this modeling. They have done this linear regression or whatever, multilinear regression. With the basis of thermodynamic derivations, they have come up with these equations. So what is the use of these equational states? If you know, let's say, suppose if I know pressure equal to temperature volume relationship, from that we will be able to estimate the coefficient of expansion. The coefficient of expansion is the partial derivative of volume with respect to temperature at a constant pressure. So if I know this equation, let's say this is one equation of state, I can get the partial derivative dou V by dou T at P. Then I can calculate coefficient of beta. At least I can get an expression in terms of pressure and temperature only. Isothermal compressibility, again the partial derivative of volume with respect to pressure. So we have this equation. I can get the partial derivative. Then I can express the compressibility factor in terms of two variables. And from this beta and K, we can find out Cp minus Cv. Then we can find out delta H, change in enthalpy, Cp dt, volume, temperature, and P. Again, everything expressed in terms of pressure and temperature, volume. Even if you take the latent heat, that is differential derivative with respect to vapor volume, liquid volume. So equation of state is a cubic equation. Like if you see, if you simplify any equation of state, non-ideal equation of state, it will become a cubic equation in terms of volume. Cubic equation means what? Every cubic equation will have three roots. So one is solid. So volume, three volumes will come, V1, V2, and V3. Three roots means three volume values will come. So one could be one represents solid line, one represents liquid line, liquid-like route, and represents vapor-like route. So depends upon the pressure, temperature conditions. We have to see whether it's solid route or liquid route or vapor route. So we can get the vapor volume and liquid volume from the cubic equation of state. And we can get differential derivative of this equation of state because P we know. If you just differentiate with respect to temperature, we get this. We can find out the latent heat. So from this slide, what I wanted to inform you is that once we have this equation of state, then we'll be able to estimate all other properties. Now, extensive thermodynamic derivations were done to express all the properties in terms of two properties, pressure, temperature, or pressure volume, or temperature volume, any two properties. Because for a single component, a single pure component, we need to define minimum two variables according to degrees of freedom. That's why the whole exercise was how to express all the properties in terms of basic properties, that is pressure, temperature, volume. So these equation of states, since we're able to predict the properties with help of this equation of state, these equation of states are called as, are used as property packages. Why we call property packages? Suppose saturation pressure, Psat. Psat, we can predict from equation of states, but it doesn't predict very well with the equation of states. So that's why one guy, Anthony, great scientist Anthony developed this Anthony equation. So we combine this PSAT data with the equational state to predict some of the properties. CPCV can also be predicted, but more than that, we have extensive experimental data for the CPCV. So CPCV, PSAT, and for these three properties, often they use this experimental data. So they combine this equational state and some of the experimental data hold together expressed as one package. So that's why we won't directly use equational state, rather they use property package. But the background, it takes the majority of information from the equational state, some of the data from the practical experiments, together they call as property packages. So in Aspen Plus or DWSIM, we have these property packages. We have this property package. One property package is Redlich-Kwong property package, and the property is SRK property package, and the property package Ping-Robinson property package, and the property package is based on the Lee-Kessler correlations. Like this, we have many such property packages are there. So I hope my explanation give you an idea how the equational state is related to the property packages. I hope you're able to understand. If any questions from your side now, you may ask me. Okay, probably no question. So this equation of states used to get the properties, all the properties, including compressibility factor, fugacity, activity coefficient, many complicated one. Now to calculate this compressibility factor, fugacity, activity coefficient, chemical potential, if the manual calculations required very it takes a huge amount of time. So that's why people have written different programs to use this equational state, very complicated line equations or very complicated correlations. And all these things are kept written in a background programs and generated this process simulator after so many years of effort. So let's go to this DWSIM and see how these property packages are used to generate these properties and how this vapor liquid equilibrium data is generated. We will see. Do you need any break for a few minutes before you proceed, or we can proceed? So you're all saying that we can proceed. So I just opened DWSIM software. As I said in the last class, it has basically two things important in the front one. One is process model, and the one is documentation. So if you want to refer all this documentation, user guide and learning resources, just click here, you will get it. So you'll go to this process modeling, create new wizard. So introduction, I should click next. Here I have to select the compounds. Here I have to select the compounds. So last class we have taken sulfuric acid and water. Sulfuric acid and water. So although sulfuric acid water is a miscible liquid mixture, usually the mist formation is significant when you heat sulfuric acid and water. So that's why usually we don't go for distillation when you deal with the sulfuric acid purification. So today, since we want to talk about class separation, vapor liquid equilibrium calculation, all the things, I want to take water and ethanol system. I want to take water ethanol system. So I just selected water component. I just selected one component as water, another component as ethanol. I have taken two components, water and ethanol. So select two components. Now, these are the property packages available to us. Black oil, Cape Open, these are the many property packages. Cool properties, and here NRTL properties. Which one to be selected? Now the question comes, which one to be selected? Can we select anything, or do you have any criteria? As I said, the equation of states when they do derivations, or when they generate this equations, they have made some assumptions. Those assumptions act as a limitations. We all know those assumptions act as a limitations. So based on those limitations, we cannot say that any property package can be used for anything. Definitely that won't give a proper result. This different property packages predicts certain components very well. For example, if you're dealing with hydrocarbon liquids in petroleum industries, then which property package will use better? So Peng-Robinson is primarily defined or derived for hydrocarbon components. So Peng-Robinson equation of state predicts very well for the hydrocarbon properties. But now the Peng-Robinson cannot predict the properties of the thick black oil come from the many of the with the crude distillation unit, or some of the units where you get the thick black oil. Peng-Robinson cannot predict it. So at that time we have to use the black oil property package. Now, if you have any simple organic solvents like ethanol, methanol, if they're in vapor form, or a gaseous form like CO2, these things, we can use SRK. If it is very high temperature, very low pressure, we can use Raoult's law property package. If we are dealing with only steam, we can use the steam tables. Now, if we have a liquids, more non-idealic behavior. If you have liquids, we prefer UNIFAC, and specifically UNIFAC liquid, and we can use this property package. Now, there is one thing called NRTL or NIST. NIST is National Institute for the Standards there in the United States. They have developed the property package based on the experimental data. So they have used experimental data and modified this UNIFAC correlations. They call NIST and NRTL. So like this, many property packages. Now, which one to select? So there's a proper guide. Is available to select which property package, because if you select wrong property package, you will get the wrong properties. You will not be able to predict the properties very well. If properties are wrong, all the calculations goes into vain. If the properties are wrong, all the calculations goes into vain. So the defining or selecting the property package greatly enhances the predictability of the many of the calculations what we do. So this is a simple slide. I also have the another slide. If you pay little attention, then you will get very quick way to understand. So if you have polar components, water liking components, of the polar, if it is non-electrolytes, let's go for figure 2. This is figure 2. If it is electrolytes, then we have to use electrolyte NRTL package, electrolyte NRTL property package, or PIDGER. So here you can see polar electrolyte. You can see electrolyte LRTL. Oh, sorry. Yeah, NRTL electrolyte. We need to select this property package. So that's property package. Now, if it is non-polar component, right? If it behaves like a real component, like non-ideal component, then we can use Peng-Robinson non-polar or RK, SRK, Redlich-Kwong, Soevi, or Lee-Kessler. You can see here non-polar components. We can use Peng-Robinson, Lee-Kessler, or we can use SRK property package. We can use this. If it is pseudo-real components, then we have to use this property package. Now, if it is polar non-electrolytes, now the classification based on the pressure, less than 10 bar pressure or higher than 10 bar pressure. If it is less than 10 bar pressure, right, and if it is less than 10 bar pressure, then we can use, you can see interaction parameters available or not, IJ, interaction parameters available or not. If interaction parameters is available, we have to go for NRTL or unique VAC. You can see here NRTL. So this is the unique VAC, and unique VAC property package, and NRTL property package. We can use it. So if it is liquid, if it is liquid, if it not liquid, Wilson and this one. And here, if it's alkylate, Unifac LLE. So very clear cut way. This simple algorithm helps you to, a simple flow sheet gives you clear details about which property package we can use it. Unfortunately, no process simulator use this algorithm to automatically, once you enter it, it doesn't automatically take you which property package you wanted it. The reason is, even though you follow this, that can give you good prediction, but we always have to compare with some of the experiment results, whether they're predicting very well or not. So in industries, before they use it, they compare with some of their experimental results. Now simple, I put you same thing in a simple way. If it is ideal gas, non-ideal, ideal gas solution, use Raoult's law property package. If it is non-ideal liquid mixes, use unique VAC or NIST. Non-ideal liquid mixes, unique VAC or NIST. Okay. If it is liquid and you want to do the high precision properties, use the cool property package. But it can take a little longer to run the simulation. If you use only water or steam, for example, boilers and other thing, use only steam tables. If it is non-ideal gas, hydrocarbons, Peng-Robinson, SRK or Lee-Kessler. Hydrocarbons with a good amount of hydrogen content, then we have these property packages. Special cases like black oils, that the thick oil leaves the crude or crude distillation unit, and such kinds, and the black oil, crude oil coming from the underground reservoirs, then we use special package called black oil. Sour water, we have hot, soft one, different these waters. For special case of waters, we can use this property. So liquids, unique VAC, NIST, gases, Peng-Robinson, SRK or Lee-Kessler. If you can remember that way, that give you click easy thing. If you go for industries where we need to be very specific, then we will get into very minute details. But for a quick way, liquids, if you want to assume it as a non-ideal behavior, unique VAC or NIST. NIST is more preferred of all the things, but you can use any of three. For non-ideal gases, preferably if it is hydrocarbons, use Peng-Robinson and this thing, or SRK. Of all the things, Peng-Robinson is predicts more better than other two, so people tend to use Peng-Robinson as a first option. I hope this made your life simple. Liquids, non-ideal, unique fact, unique fact. Gases, non-ideal, if it is hydrocarbons, this one. That way, if it is non-hydrocarbons, we might go for SRK. If it is hydrocarbons, predominantly Peng-Robinson. That way, we can easily select it. So we will see this how to generate this VLE data. Now, this is the vapor liquid equilibrium data which I discussed just now. Temperature versus mole fraction of ethanol. Mole fraction of ethanol. Here, ethanol is high volatile component. So x-axis is mole fraction of ethanol is kept, and y-axis is temperature. And here pure water, that is 0 when x equal to 0, that is no high volatile component, only low volatile component, that is water. The boiling point is 373, and this is the boiling point of ethanol, slightly less than, or it's around 351 Kelvin. And this is the experimental VLE data. This is the experimental VLE data, and it shows that above when the mole fraction is higher than 0.82 or higher than 0.9, this will form an azeotrope. Azeotrope means what? Once you heat it, the weight, the composition doesn't change. It will have the same composition. Vapor and liquid both in the same composition. The vapor and liquid will be same composition. X equal to Y. Azeotrope means X equal to Y. But if you predict VLE data of ethanol water system using Raoult's law, it will come like this. Using this Raoult's law, it will come like, and it's totally different. You know, this is experimental. This is real one. It will be totally different. So that is why often we don't want to use an ideal gas equational state or ideal solution equational state. So that is where comes this non-ideal gas equations or non-ideal equational states. That is where this importance of this property package comes into picture. Importance of these property packages comes into picture. So let's see. Let's go to this DWSIM. Since I have selected ethanol and water, what property package I should select? Can someone from the student side? Now we have selected ethanol and water. Both are liquids. Now I need to select a property package. What property package should I select? Maybe I'll put this slide.
Sir, NIST.
I have kept water ethanol system, and I need to select property package. Which property package I should select?
NIST. Modified, unified.
What happened? Disconnect. Are you understand question, students?
Sir, NIST.
Hello?
Yes, sir.
Yeah, which one, Varun?
NIST.
NIST, yeah. So, you can select NIST. As I said, we can select unique fact, NST. NST is more preferred one of the three. Select NIST, modified unique fact ST, and I also want to compare with ideal how it looks like. So I also select Raoult's law for this. Next, so I want to use SI system, SI unit system. I have discussed in the last class. This. So the first thing is material stream. So as soon as you click on that material stream, it comes here. So this is the feed stream. The feed stream. And here the property package selected is NIST, NIST, NIST. Now we have input data and stream conditions. Input data, stream conditions. This is flash spec, flash specifications. That means temperature and pressure. Are you defining temperature and pressure? As I said, for a pure component, if you want to estimate the properties, we need to define the two properties. It could be temperature, pressure, it could be temperature volume, or it could be pressure volume, any two. Okay. So that is where it comes in flash specification. So this is temperature pressure. If I drop down, I can select pressure and enthalpy based. I can select pressure and entropy based. I can select pressure and vapor fraction based. And I can specify temperature and vapor fraction. Here they have only option of these are the flash specifications, total 5. That is more practical oriented, but you can get anything. You can get any other like temperature volume, pressure volume, any other flash specifications are possible. But common process simulators, for the ease of convenience, they use this, and this is practically related to all the systems, temperature and pressure. So we need to specify what temperature of the stream or what temperature at which the liquid is present or the component is present, at what pressure this component is present. So this is the input data, stream conditions, the flash specifications. Why are we doing this? Why are we making this flash specification? I hope you understand. This comes from the degrees of freedom or the number of independent parameters needs to be defined. Compound amounts. As soon as you take two components, by default, it takes us 50%, 50%. It takes us 50%, 50%. If you want to change it, we can always change it. Let's say 0.4. If it is 0.4, this has to be, it automatically doesn't change this to 0.6. We have to manually change it. Once you enter both values, we need to click accept. Then only the values will change. But this is the base mole fraction. But you can define mass fraction, mole flows, mass flows, liquid flows, or volumetric flow rates, molarities. You can define any way. You want it. So this is the feed stream. Ethanol water feed stream is going. Now we want to do the separator. This gas liquid separator, this gas liquid separator is a typical flash separator. As I said in the last class, something is highlighted in red means what? Can anyone say? Students, those who not answered earlier. If something in red color in the software, what it means?
It has not been defined completely.
Yes, it's not been defined completely. Very good, Andrija. So something is missing. So that what is missing, what are the minimum requirements, we can know by the user guide, or by if you as go to the classes, my classes, you will understand what are the minimum requirements and what are the important things. So this is today we're doing the flash separation, flash separator, So the flash separator needs at least one feed because some feed has to go inside and one vapor stream has to come outside and one liquid stream has to come outside. Right? This is minimum requirement and we need to supply some energy to this one. We need to supply some energy to this one. If I wanted to make it inactive, let's say make a big flow sheet, suddenly I don't want to use flash separator, we can make it inactive and you can make it active just by clicking this symbol, active and inactive. Inactive means doesn't participate in the calculations. So one inlet stream is required. So the feed stream we have fed. So this is the feed. You can connect multiple inlet streams. You can connect multiple inlet streams to this flash separator. Is up to 6 streams is allowed in the software. Now to create, as I said, one vapor stream, one liquid stream has to come out. So what I need to do to create one vapor stream and one liquid stream? How do I get vapor stream, liquid stream there? Anyone from student side?
Add material stream.
Add material stream. So we can take the material stream and you can drag it. Another way is if you click here, it'll create and connect the stream. You can see the symbol here, yellow color one. If I click here, it will also create and connect the stream automatically. One way is you can drag the material stream and connect it. Another way is you can just click on this one. You can see just clicked here and the stream 3 is connected automatically. It connect and create. When I click here, the stream properties is opened here. So I will just say vapor stream. I just say vapor stream. Now again I'll go to this and here light liquid stream, heavy liquid stream. If you have two liquids are there, then we have light liquid, heavy liquid, depends upon their boiling point conditions. But here we are taking only one liquid stream. So I just click here, create and connect. So as soon as we have done this, it turned into blue color. That means we have defined the minimum things. We have defined the minimum things required for this one. Liquid stream, and this is flash separator. Right. Now, if you see in the flash separator, we have defined it to be, the pressure, defined it to be atmospheric pressure. By default, it takes atmospheric pressure. Now, I have feed, right? I have feed. The feed temperature is 298 Kelvin and feed pressure is 101325. So at 298 Kelvin, and 1 atmospheric pressure, ethanol plus water will be in liquid state. If I send this flash separator, how much amount of vapor will come and how much amount of liquid will come? Can anyone guess? I hope you're understanding the problem statement. I have ethanol water stream, which is at 298 Kelvin, 1 atmospheric pressure. This is a liquid state. I have introduced that into flash separator. I didn't do any heating. Okay. How much amount of vapor and how much amount of liquid will come? Soumik, can you answer?
Yes, sir.
Yeah, how much amount of liquid will come and how much amount of vapor will come? Soumik, please answer. Will it form any vapor at that conditions?
So inside the separator, the pressure drops, then it will form vapor.
If you don't heat at all, even if let's say you have liquid from small tank to big tank, if you pour it, if it doesn't, if it is room temperature, will it form any amount of vapor? Will the pressure difference makes any big difference?
No, sir, I don't think.
Yeah. So we are actually not reducing pressure. We're just introducing water from a small pipeline in the big tank. If it's at saturated temperature, then only vapor formation, all these things can take place. If both are at liquid state, if the temperature is lower than saturation temperature, if the temperature is lower than saturation temperature, what is saturation temperature? What is saturation temperature for a liquid? Let's say we have liquid, single liquid or liquid mixture. What we call saturation temperature? Tsat or Psat. Tsat refers to Tsat. We call it as boiling point temperature for a single component. Tsat refers to boiling point temperature for a single component. For mixers, the Tsat would be bubble point, because for a mixers there is no one individual thing. Greater than or equal to bubble point or dew point, there is no, for mixer there is nothing called exact specific thing. So dew point temperature. So often saturation refers to the boiling point temperature for a single component. For mixers, if it is above, greater than or equal to bubble point temperature, that we call it is under the saturation conditions. Saturation condition. Since at 1 atmosphere, both of neither ethanol nor water bubbles, So from the flash separator, liquid flow rate will be liquid mass equal to feed mass. Vapor will be zero. Vapor will be zero. Flash separation starts only if the temperature is saturation temperature or the temperature is equal to the bubble point temperature. If the temperature of the feed liquid in the flash separator is lower than the saturation temperature or lower than the bubble point temperature, you will expect no vapor to come out. So that's why we have a heater here that should bring to the near saturation temperature. That's why every flash separator will have a heater here. If you have no heating, if the temperature is in the liquid state or the temperature is lower than the saturation temperature or the bubble point temperature, then no separation is expected or very, very minimal separation. So since here we have the feed at room temperature, at atmospheric pressure, this compounds, and we solve the flow sheet. Now we can see vapor. You can see vapor mass flow is zero. Now if you see liquid, You can see liquid mass flow is 1 here, and feed mass flow is also 1 here. Feed mass flow is also 1 here. Let's see the table. How do we get the table here? Property table. Anyone remember based on yesterday discussion? If you want to display the values, anyone remember what should I do?
So from insert.
Oh yes, very good. So insert master property table. It will come here. If you do double click, we wanted to see feed, vapor, liquid conditions. So we want to see temperature and mass flows. Let's see, we wanted to see these two. Now we can see the feed is 1 kg per second, the liquid is 1 kg per second, and the vapor is 0. The vapor is 0. Now I want to change the feed temperature. Let's say I change the feed temperature 310 Kelvin. Now flow sheet, we solve the flow sheet, and since the boiling point temperature of ethanol I showed you is 351. The boiling point temperature ethanol is close to 351. If the temperature should be higher than 351, then only the vapor formation will take place. Then only we'll get certain amount of vapor from the flash separator. So at 310 Kelvin, 0 and 1. Let's say I'll make it 352. 352. Still, I don't see any amount of vapor because just bubble point temperature. If I go to 360, we go to 360. If I go to 360, and I can see, now we can see the feed certain flow rate and mass flow is there in the vapor, and you can click on the vapor and you can see the compound amounts. Now the liquid is becoming 0, right? So this totally varies. So the totally varies between vapor and liquid conditions. Totally varies between the temperature, vapor, liquid conditions. But now I think so. Now I wanted to show you one more thing. Utilities. Add utility. Add utility. So using this add utility option, we can generate phase envelopes, binary phase envelopes, and ternary phase envelopes. If you want to generate vapor liquid equilibrium data, we use binary phase envelopes. If you use liquid equilibrium data, we use ternary phase envelopes. So binary phase envelopes of feed we wanted to generate. We want to generate the binary phase envelopes of the feed. So we click utility, then we get this. So earlier I showed you files. This is the flow sheet, dynamic manager, and new tab will open, which is binary envelope. So this utility you can see here in the top on file, edit, and here we have a utility. This utility is used to create this binary phase and ternary phase envelopes. That is vapor liquid equilibrium data and liquid equilibrium data. So we have compound 1. I will select ethanol, and compound 2 is water. So compound 1 is high volatile component, and compound 2 is low volatile component. So we can generate TXY data, PXY data, and we need to select, since I select the binary phase envelope, I can only do VLE. If you do, if you want to do liquid equilibrium data, we can select LLE also. So x-axis mole fraction, and the pressure is 1 atmospheric pressure, and the temperature varies as we have the TXY data, and the fraction varies from 0 to 1. 0 to 1, and here I have selected the property packages, this property package, So I click calculate, and it generated the vapor liquid equilibrium data. And x-axis we have the mole fraction of ethanol varying from 0 to 1, and y-axis is the temperature, and this is the you can see the blue line is the bubble points, and this orange line will be the dew point temperature. Now this is the generating the vapor liquid equilibrium data using this property package NIST. So if I just copy this. So I just did the print screen. I just copied this. If I use Raoult's law, and this is the vapor liquid equilibrium data based on the Raoult's law. So Control S. I will just save it. So this is the Raoult's law, VLE data from the Raoult's law, and this is the VLE data from the NIST. Now we can see here, this is the Raoult's law, and it's matching with this one, Raoult's law 1. And here, this is the experimental data, and now we can see NIST data, and at least you can see above 0.8, and to be very precise, above 0.9, you can see azeotrope formation. You can see azeotrope is trying to build above 0.8, but perfect azeotrope forms at close to 0.9, and you can observe same thing using the NIST data prediction also. Above 0.8 onward, this is very close, and good amount of separation is up to 0.5. You can see 0.5 separation is taking place. So whenever we want to use a property package, we will have to compare these predictions from this property package from the experimental data. Whichever property package matches very close with the experimental data, we will have to use that property package. Some amount of background work is required if you want to use this process simulator for an industrial application. So this is about getting the VLE data using this different property package. You will, if you get time, maybe after the class, you can open your thermodynamics book and see how to generate this VLE data using this UniFact method. You will see that it will have a lot of complicated equations, and if you want to do this using manual calculation, it is possible, but it takes a lot of time. So with this interface, with this process simulators, by doing this, by running this code, by people have written a code and runs in the background and generates this data for us, which makes our life is much easier, more easier. There's another now if you take, even though we have this non-ideal equation of state, unique vac, and NIST one, for some liquid-liquid mixers, unifac method predicts better. For some liquid mixers, unique vac estimates better than the NIST calculation, NIST data. So we can't just say use NIST by default. We use NIST as a theoretical or as a class point of view. But if you have to use this process simulator for an industrial application, we have to check which of these property packages giving you good predicting, good estimation of the experimental data, which is close to experimental data, that we have to use it. Then you may ask, why can't we use experimental data directly? Why can't we use experimental data directly? Why do we need to use the property package? Now let's say to generate this data from 0.1 to 0.1, if you have to do all the intermediate points, let's say 0.05, 0.15, 0.25, 0.35 at different temperature, it is very, very difficult. It is very, very difficult to do all the intermediate points, So people do some experiments, then they develop these models that can predict, so that gives a approximate correlation to the experimental data that makes our life more easy. We don't need to do lot of experiment. It is time consuming, energy expensive, and it is almost practically difficult to do. Just for ethanol water, if we have to generate this data, complete data, we have to do lot of experiments. But if you develop model, then you can do few experiments, around 5 experiments, then you can get all the intermediate interpolations. So that's why the modeling helps us to find out intricate details, which we don't need to do lot of practical experiments. But often these models come from the theoretical background, also come from the statistical fitting data, that is linear regression or multi-nonlinear regression. Techniques were used long back to generate these models. So if we want to close, this is paint one. Want to close, you can simply close this binding envelope and you can go back to the flow sheet. So we can use compound separator. Here one inlet stream, feed, and outlet stream vapor, outlet stream liquid, and we can connect an energy stream. Which we can heat it at the intermediate temperatures. We can provide energy. We can put 0 if you don't want to give any external energy input during the process. But if you want to give any heat during the separation, you can reduce amount of heat. To this one. So we can vary temperature, we can vary pressure, and we can see how much liquid, how much vapor that can come out from the system. We can do all these calculations. But for some reason, this flash separator is not giving very good prediction of the vapor and liquid properties. Maybe I selected wrong. Okay, so small. I expected to be better prediction because when I put it temperature higher than bubble point, the vapor is showing 0, liquid is using 1. I don't understand why it is, why the software behaving. Probably I will figure it out and I will let you know in the next class why this is not giving, and I will find out the right procedure and I will let you know. But the whatever explained for the flash separator, flash calculations, and vapor liquid equilibrium data, all the things, I think they're all right. So this flash calculations, why it is not exactly showing the vapor flow rate, I will let you know next class. And that's all from me for today. If you have any questions, let me know. So mainly I've explained property packages, vapor liquid equilibrium data, and equation of states, and how to choose the equation of states, and what is the need of selecting the right property package. That I have discussed in the today's class. And flash separator, why it's not predicting very well, that I will tell you in the next class. If you have any questions, please let me know. Otherwise, we can stop here. Hope you're able to understand and learn something. And thank you. Have a great day and see you next week.
Thank you, sir.
Thank you.